Hello, we're examining the curious sociology of pure mathematics, where, strangely, we believe really crazy things here in pure mathematics. And these beliefs are like foundational beliefs, supported by very little evidence, but a lot of wishful thinking. And principal among these fantastic beliefs is the idea that we can go to infinity, that we can take a limit, which ultimately amounts to we're able to do an infinite number of things and complete the job and get an output that we can then use for further machinations. Today we're going to examine the consequences of this point of view by cracking the most famous unsolved problem in mathematics, the Riemann hypothesis. So I'm going to tell you very roughly what the Riemann hypothesis is, in a way that's hopefully accessible to a wide audience. Then I'm going to talk about an alternate formulation of it due to Geoffrey Lagarias, one of many alternate reformulations. And I'm going to show you how we can actually crack this problem by actually making a computation. That is, assuming these superhuman powers that pure mathematicians ascribe to themselves. All right, so we're going to have a little bit of fun today. So let's start with the zeta function, which is the principal object in the Riemann hypothesis. So this is ostensibly a function. And you start by taking a natural number, like 2, 3, 4, etc., and forming this sum. You look at the sum of reciprocal powers of the natural numbers. So 1 over 1 to the n, plus 1 over 2 to the n, plus 1 over 3 to the n, and so on. Okay? And here is the mathematical symbol that we use for such a summation. Summation k equals 1 to infinity of 1 over k to the n. Now, it's important to recognize this is not a finite sum, okay? This is meant to be an infinite sum. So we do not stop increasing the sizes of these denominators. They just keep on getting bigger and bigger and bigger. So correspondingly, these terms that we're adding get smaller and smaller and smaller, but we still have to keep on adding them. So there's an infinite amount of work to be done in creating such a sum. And pretty well every number theorist in the world, every analyst in the world says, yes, this makes sense. This is a bona fide definition. This really does define what's called a real number. And we're in a position to talk about this real number. And that's giving us the so-called zeta function. Now, I have to object. I don't believe this. I don't buy this. For me, arithmetic is what you do with a finite number of objects. You perform a finite number of calculations, and then you get an answer. So for me, the idea of computation is the same as what a computer would do, right? A computer also performs a finite number of computations and then gives you an answer. So me and the computer world are quite aligned. So I may not have a lot of mathematical colleagues that agree with me, but I have a lot of computers that are very much on the same page with me. Okay, so let's have a look at an example, all right? Let's consider zeta of 5. So that means we replace the n here with 5. We're talking about 1 over 1 to the 5 plus 1 over 2 to the 5 plus 1 over 3 to the 5, etc. Okay, so as a warm-up, why don't we go a little ways down this infinite road? Maybe to 15. So let's take the sum from k equals 1 to 15 of 1 over k to the 5. So we're going to take all the terms from 1 over 1 to the 5 all the way up to 1 over 15 to the 5. Well, that's a finite sum. That's something that we can do. That's something our computers can do. In fact, my computer has done it. There is the result of the first 15 terms of this series as a fraction, because that's what it is. It's a bunch of fractions added together, so you get another fraction. But it's not so easy to tell how big this thing is exactly. So my computer can also convert it to an approximate decimal. Okay? So since it's a fraction, the decimal expansion would be repeating, presumably with quite a long period. Okay? But at first it looks like this, so it's 1.0369234, and etc., etc. Okay, so that's up to 15. Now, you can kind of see that you don't have to go too much further. And these denominators here are getting pretty big because we're taking fifth powers. So these numbers that we're adding here are really small. They have big denominators. So when we're doing this fraction arithmetic, this thing is really getting big. Okay? So if we watch this thing on some, say, infinite screen, okay, this thing would be getting bigger and bigger and bigger with every step as we add more and more terms. But there wouldn't be a very clear sense of this thing converging to anything. We wouldn't be able to see, it's approaching something. It's only when we convert it to like a decimal like this that we have a sense of this thing approaching something, because as we add more and more terms, what's going to happen is that the initial terms here are going to sort of stabilize, and we're only going to be sort of changing the entries which are further and further out here. Okay, so there's some sense that as you keep going, this decimal sort of converges or stabilizes towards some infinite decimal. So that's the usual story. It's a story that I don't buy, because in fact, long before you get to infinity, say, if we replace this 15 with, say, 10 to the 10 to the 10 to the 10, just a stack of 4 tens, one on top of the other in an exponential fashion, already at that stage, one can easily see that the sizes of these fractions that we're getting are already far beyond the size of the known universe to encompass. Even if the entire universe was used as a massive hard drive with data points crammed in on the Planck scale. So there's no question that long before we get to infinity, the thing that we're calculating here blows up, and the universe that we are in is no longer capable, even theoretically, of encompassing that. So the pure mathematician who wants to justify this has to have some shift in their minds. They have to say something, well, okay, what we're going to do is we're going to kind of pretend that this is all happening in some alternate universe. We're imagining some other universe, say outside our universe, which has the very convenient property that it's infinitely large. Not like our universe. Our universe is finite, probably. Okay? No, we have to imagine these universes which are infinitely large, and therefore they contain enough memory space to be able to hold these huge things as they blow out of our universe. So there's a lot of essentially religious sort of dogma associated to this, right? It's almost like biblical proportions, the kind of wonderful things that we have to postulate in order for this story to make even a shred of sense. And it's far removed from computational reality, right? There's no way a computer can deal with anything like this once this number here gets to the order of 10 to the 10 to the 10 to the 10. Least of all when it actually is approaching infinity in a serious fashion. But in a spirit of generosity, let us for this lecture embrace the standard orthodoxy and pretend, as my fellow mathematicians do, that actually these things do make sense, and that this series defining the zeta function is actually well defined. How does the story unfold after that? Okay, well, the idea is here is a number line. There's 0, there's 1, there's 2, there's 3, etc. And we think of this zeta function as giving us values for any point in here, right? Well, we started with 5. And we got something like 1.036927. Now we're assuming, yes, there's an infinite decimal here that's associated with the zeta function's value at 5. And correspondingly, we could get numbers 4, 3, and 2, etc. And rather remarkably, this connects with beautiful formulas of Euler, which I also have some qualms with, but I do admit that there's something really beautiful happening under the bonnet here, but we just haven't been able to say yet what it actually is. But his results amount to the fact that you can create formulas for the zeta function's values at these even integers. In terms of powers of pi, like this one's pi squared over 6, this one's pi to the 4th over 9, and some other remarkable numbers coming from Bernoulli. But the odd ones here are much harder to say anything precise about. But we're going to assume now that this zeta function, okay, expression, works not just for natural numbers n, but even for fractional values. Okay, so those 1 over integer to the n, we're now going to suppose that even if we replace the n with a fraction, like maybe 2 over 9, that we can still write out that series and make that calculation. So that's a huge additional assumption, because now we're supposing that, if we have something like 4 to the 2 over 9, we're getting something irrational here. We're getting something that's not itself a finite operation, right? To calculate 4 to the 2 to the 9, it's like the 9th root of 16. That itself is an infinite operation. It can't be done in a finite amount of time. Your computer cannot do that exactly. So the extension of the zeta function to, say, rational values here on the number line is already a very big extension, which we're also going to happily assume we can do. And then it turns out that if we think about this number line as being embedded in the complex plane, so we have another direction with this complex number I, whose main property is that I squared equals 1, then it turns out that this zeta function ostensibly can sort of be extended to complex values. So we can associate a meaning to this infinite series even when the exponents n that are appearing in the denominators are replaced with more general complex numbers. Okay. And it turns out that those series converge in a sense that the analysts like, sort of in this portion of the complex plane. Okay, and then it gets a little bit complicated. There's something called analytic continuation that allows you to take certain formulas for this thing over here and sort of extend that formula to extend the function's values essentially to the entire plane. Okay, so it turns out to be then some kind of symmetry already observed by Euler, or I guess maybe Riemann, about this critical line where the horizontal component is a half. That plays a very important role in this subject. So now we're imagining this complex valued function, which is an extension of the zeta function that we first were considering, to complex number values. And it turns out that it has some interesting things. So at this point 1, there's a kind of a blow up. At the negative even numbers, like -2, -4, etc., it turns out that there's zeros. Okay, this analytic continuation has some zeros there. They're called trivial zeros because they're quite predictable. So the Riemann hypothesis then amounts to the following statement, that all the other zeros, like that is the ones that are not these trivial ones on the negative axis here, they are all happening on the line where the real part is equal to a half. Okay, so there's a whole bunch of these zeros ostensibly, and they're all on this line here. Now this is not the scale; they're not exactly like this. I'm just picturing them to give you an idea, right? So that's the main conjecture, or the most famous conjecture or unsolved problem in modern mathematics, is that this extended Riemann zeta function has all its non-trivial zeros on this critical line. And when you state it this way, it sounds really obscure and so on, but in fact, this has huge connections with prime numbers and all kinds of interesting questions in number theory. And I should say, that there's, I don't want to say that the Riemann hypothesis is nonsense. No, it's really tackling a really delicate and remarkable aspect of the world in which we live. Okay, I have no question about that, but I question the language and the sort of overarching analytic framework in which it is currently presented. Right? So I believe there's a very interesting phenomena there, but that we have not yet put our finger on how to even express this phenomena in the right way. Okay, so I just want to make that clear, that there is something going on. There's something very deep, very profound, very interesting going on with the Riemann hypothesis situation. It's just that we haven't yet understood how to even formulate it in an exact, precise way. Now, because this problem has attracted so much attention since it was formulated by Bernard Riemann in the middle of the 19th century, Many people have discovered alternate formulations of it, which again is some kind of indicator of the intrinsic interest of this problem. It is really a very interesting problem, whatever that actually is. Okay, and here is one of actually many reformulations of it. It's one that I particularly like. I think it's very attractive. It was found by Jeffrey Lagarias in 2002 in the American Mathematical Monthly. It's written up. And it's concerning these numbers called harmonic numbers, which are just rational numbers. Okay, so they are sums of reciprocals, just 1 over j. J equals 1 to n. It's like 1 over 1 plus 1 over 2 plus 1 over 3. That's the third harmonic number, Hn. Okay, and here is his reformulation of the Riemann hypothesis, that for any natural number n, 1, 2, 3, etc., this inequality holds. On the left-hand side, we have sigma of n. It's a number theoretical function. It's the sum of all the divisors of n. So if you have a number like 6, its divisors are 1, 2, 3, and 6. Those are all the natural numbers which divide 6. And the sum of those things is 1 plus 2 plus 3 plus 6. That's 12. It's actually quite interesting because that's exactly twice the number. That makes 6 a perfect number. Okay, so that's what's on the left-hand side. That finite sum, it's just a natural number. Okay, on the right-hand side, we have this Hn. Okay, n is the same number there, so it's the nth harmonic number. And then this expression here involving the product of the exp of Hn with log of Hn. So I have to remind you, what are exp and log? Well, these are also functions, actually very familiar and sort of elementary functions in analysis, but still they have this infinite nature which I object to ultimately. But anyway, here's the standard definition. So exp of x is defined to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial. 3 factorial means 1 times 2 times 3. Okay, and then you keep on going. And again, this is an infinite series, so it keeps on going. So you have to take all of these terms and you have to perform this infinite amount of arithmetic. Okay, the terms are typically getting smaller because these factorials get big. So the terms are getting smaller and hopefully you're converging to something. So that's the standard definition of the exponential function. The log function, well, here's one formula for it. Log of 1 minus x is also given by a series, something like this. X plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4. There's no factorials, just simple denominators there. And this particular formula is known to sort of work only when x is in a nice range close to 0, when it's between -1 and 1. So you can think about this as being the definition of log, and other values of logs can be sort of relatively easily converted to this one. Okay, so let us temporarily, for the purposes of this talk, let me assume these superhuman powers that analysts and number theorists like to give themselves, which is the ability to actually perform calculations like this. So I'm going to suppose that, yes, I actually can make sense of this, that this is a well-defined thing for me. I want to find x of something. I just take this series, I plug in values for x here, and I perform this infinite amount of work. That, yes, it requires going outside the universe because, again, the same story happens as these numbers go further and further. Everything gets big. Things blow up in our universe. There's no way we can do this in our own universe. So we have to imagine this all happening in some alternate universe which has an infinite amount of room in it, infinite amount of computing power available, infinite amount of patience and time. Well, maybe not time. We're going to assume that we can do all this in a finite amount of time. If you or I had to do this, well, obviously we would just have to keep on going. But we're going to assume that, no, we can do this in a finite amount of time. And same thing for this expression here. So that's really the core. That assumption is, in fact, so powerful, okay, that I'm trying to convince you it actually essentially trivializes so much of mathematics. And it essentially trivializes this problem too. Okay? So this assumption, which is built in to even understanding and appreciating what this statement is, this assumption is already enough to essentially kill these problems like this. I also should have said that another part of the thing is that there should be equality, strict equality, when we have equal sign there, precisely when n equals 1. When n is 1, this is 1, this is 1, this is something, and this is 0, so we get 1 equals 1. Okay? But otherwise, there's strict inequality here. So this is Lagarias' restatement, and let's see how we can address this, because this is a lot easier, right? We don't have the complex numbers, we don't have this mysterious Zeta function, we don't have to perform analytic continuations, we don't have to know fancy formulas about how these functions sort of behave with respect to the critical line. It's a relatively simple expression, assuming we are allowed to have infinite computational power to get at this exp and to get at this log. Those are the two big assumptions that we're actually making here. All right, so please watch carefully, nothing up the sleeves, all right? So here is what we want to establish, that for all natural numbers n bigger than 1, that we have this strict inequality between this sum of divisors and this expression hn plus exp hn times log hn. Let's refer to the statement's truth value as p of n. So p of n will be a Boolean expression, or it's just either 0 or 1, depending on whether this statement is false or true. So for a given value n, if the statement is false, then p of n has value 0, and if it's true, it has value 1. So to make things explicit, let's have a look when n equals 6. When n equals 6, well, we've seen that this thing here is sum of the divisors, that's equal to 12. Hn is then the sum of 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6. That is 49 over 20. So what we have to prove is that 12 is less than 49 over 20 plus exp of 49 over 20 times log of 49 over 20. So for this to make sense, we have to be able to compute exp of 49 over 20, right? That's implicit here, that this actually has a legitimate meaning, not in an approximate fashion like an applied mathematician would want. Okay? Applied mathematician does not care about infinite decimals. An applied mathematician thinks about this differently. It's just a finite number of terms, it's a convenient truncation of that infinite series that I showed you, and similarly for the log. No, but we're approaching this as pure mathematicians. So we're going to suppose, because of these superhuman powers that we've currently adopted, that we know exactly what this means and that this has a legitimate meaning for us. Yes, that series can be totaled, that infinite computation can be done, and there's the result. And there's the result. Okay, so we get some infinite decimal. And by actually taking truncations, okay, my computer can't do this calculation, but it can do it approximately. It can take truncations of this and truncations of that, reducing us from infinite arithmetic to finite rational arithmetic. And then it can give this approximation to the right-hand side, 12.834178, etc. And that's enough for us to see that, yes, indeed, this 12 is less than this value here. Now, if I was really able to do this infinite amount of work, I could actually compute this exactly, I could compute this exactly, and I could obtain this thing here, not just to 20 decimal places, but to an infinite amount of decimal places. That's what I'm assuming, just temporarily, that I can do that. Okay, so the conclusion is that when n is 6, this Boolean expression p of 6 has the value 1, because the equality of Lagarias is true. And now, ladies and gentlemen, taking the powers that I have been temporarily given, I am going to compute this crucial quantity. Let's call it W sub RH, RH for Riemann hypothesis. It is the product. Here's another sign, like a summation sign. It means take a product of things from n equals 2 to infinity of p of n. So we take p of 2 times p of 3 times p of 4, etc. So what does that mean? Well, it means that I'm able to do an infinite number of things, right? So I've just calculated p of 6 for you. But I'm going to start now with p of 2, and I'm going to calculate p of 2, making an infinite computation. I'm going to calculate p of 3, make an infinite computation, check the equality, p of 4, p of 5, p of 6. There's an infinite number of tasks that I have to do. Each of them requires an infinite amount of work. But hey, I can do an infinite number of things in a finite amount of time. So I can do all of those things. So I can make a list. I can tabulate what is P of 2, what is P of 3, what is P of 4, and I have this infinite list of these Boolean truth values right there. Each of them is either 1 or 0. And what I'm doing here in this final step is I'm just multiplying all of these together. Another infinite task, but hey, we're all capable of doing infinite tasks, aren't we? Sure. So 1 times 1 times 1 times 1. Well, if they're all 1s, we're going to get 1. If one of them is 0, the whole thing is killed and we get 0. So in fact, once we get to 0, we know what the output is, 0. We don't even have to carry on to the end. But carrying on to the end doesn't bother us. It's just doing an infinite number of things. Hey, we're assuming that in even defining this and even accepting that this is a valid object. Okay, so this is a number. This is the result of a computation, okay, which in principle is really not that much different from this quantity here. X of 49 over 20, whatever that is. That is a legitimate object in modern number theory and analysis. If a problem ends up with the answer is X of 49 over 20, everyone will say, oh good, we've got an answer. You may stop. That's considered a final, complete answer. Nobody asked, yeah, but what actually is this? Show us the infinitesimal. No, everybody is polite enough to know not to ask that question, okay? Except perhaps for me. But everybody else is accepting that we're just applying exactly the same criterion here. There's no need of asking, what is this actual value? I don't have to tell you. This is an expression for the truth value of the Riemann hypothesis. Is it true or false? The answer is, it is this. So, the consequences here, I hope that what you're going to get out of this is that this assumption that we can do an infinite number of things, which is implicit in not just the definition of x, the definition of log, or the definition of the zeta function, but it's implicit in so much of modern mathematics, not just analysis and number theory. This assumption is so strong that it basically trivializes a lot of mathematics. And somehow people haven't put this together. People have not wanted to see that this particular assumption that we can do this has all these, really distorting consequences. But that's just the logical reality of it. So if we want a proper mathematics, we have to become much more modest about what we actually want to assume about ourselves. And a good way of proceeding is to, well, why don't we just assume that we can do what we actually can do? And if there's any question about that, why don't we just peg ourselves to what our computers can do? That's very cut and dried, and we can all agree.